Hi everyone! We're excited to share our research on evaluating the impact of stratified bootstrapping on low-resolution grayscale image classification. It might sound technical, but at its core, it's about improving how machines recognize blurry or low-quality images, using a method that's smarter about how it learns. We found that the existing literature mostly focuses on high-resolution or colored images. But when we look at simpler, low-res data, there's a gap in how models are trained and optimized. That's exactly what we wanted to explore and improve. Think about it like this. If you're trying to recognize someone's outfit in a pixelated photo, it's tough. Now imagine teaching a computer to do that. The missing detail leads to poor accuracy. And when the image quality changes from one photo to the next, it becomes even harder. Techniques we usually rely on, like dropout or L2 regularization, don't always work well here. They're great when the data is clean and clear. But when it's noisy or low-res, they can miss important patterns. They also assume there's enough variation in the data to learn from, which isn't the case in limited grayscale images. That's why we had to think beyond the usual methods. So image quality really matters. In low-resolution images, important features can get lost in the noise. That's why it's harder for models to learn what makes one class different from another. Even small amounts of blur or compression can hide the key patterns a model needs. That's why boosting image quality isn't always an option. We have to adapt how the model learns instead. Our approach uses stratified bootstrapping. Sounds fancy, but it just means we resample our data in a way that keeps all the classes balanced. Why does that matter? Because balanced training helps the model learn more fairly and improves its performance when it sees new, unseen images. We used 3 datasets: Fashion-MNIST, simple clothing images; Sci-Far-10, color images converted to grayscale; and Chest-MNIST, medical images of chest conditions. We normalized, reshaped, and sampled everything to make sure our tests were fair and consistent. We trained 3 versions of several neural networks: a basic one with no special tricks, one using traditional regularization, one with stratified bootstrapping. This helped us clearly compare how well each method worked across different types of data. By using the same architecture and parameters across these strategies, we ensured that the only changing factor was the training technique. Here's the cool part. In the Fashion-MNIST dataset, stratified bootstrapping really worked. Accuracy went up, and the model was more reliable, especially in models like all CNNs. It also improved calibration, which means the model became more confident in its predictions. That's a big deal when it comes to building trust in AI systems. But it wasn't a win across the board. In Sci-Far-10 and Chest-MNIST, regularization performed better. These datasets are more complex, with more subtle differences between images, and it turns out bootstrapping alone wasn't enough. This shows that one technique isn't always better, it depends on the context. In messier datasets, traditional tools still play a valuable role. So what did we learn? Stratified bootstrapping helps in structured, simpler datasets, but in harder cases where the data is messy or detailed, traditional methods still hold their ground. Also, bootstrapping needs more computing power, which is something to think about if you're using deeper models. Ultimately, choosing the right strategy depends on both your dataset and your model. There's no one-size-fits-all solution. Thanks so much for watching. We hope this gave you a better understanding of how stratified bootstrapping fits into image classification and how it could be used in future research. Feel free to reach out if you have questions or want to explore this topic further. We'd love to hear your thoughts.